Boom. All right, welcome back to the second part of stoichiometry. And that is stoichiometry of solution. In the last step, we're able to look at the mole concept, we look at percentage yield, we look at limiting reagents, okay? So now we are hitting stoichiometry of solutions. The concept of molality, and normality. Very, very key. Stoichiometry of solutions. So first, what is a solution? Very, very important question. What is a solution? A solution is simply a mixture of two basic components, which are the solids and the solvent. When you have a solid in the presence of a solvent, it forms what we call a solution. And that invariably means that solution is equal to solid plus solvent. A solution can exist in three states, just like the three states of matter. They can exist as solid, they can exist as liquid, they can even exist as gases. Yes, a gas solution, a solid solution, a liquid solution. Those three states of matter have solutions in those forms. However, the most common states of solution is the liquid state. Yeah, the liquid state is the most common state of solution. So in describing solutions, the component that holds the physical state of matter of the solution is called the solvent. What is that component that holds the physical state of matter of that solution? You call it the solvent. If that solvent is liquid, automatically the solution is liquid. If that solvent is solid, automatically the solution is solid. If that solvent is gaseous, automatically that solution is gaseous. You get it? So that particular component that physically holds the state of matter of the solution is referred to as the solvent. While the component that the solvent receives is called the solid, right? Good. I give you a typical example. I have sugar solution. I pour grains of sugar into water to form sugar solution. That is a solution, not sugar solvent. You get it? The solution is sugar and water. The solvent is pure water, while the solid is the grain of sugar. Right? Good. Now, let's go into some little facts you need to know as far as stoichiometry of solutions is concerned. Number one, the percentage by mass of solid in a solution. The percentage by mass of solid in a solution is simply given by the mass of the solid all over the mass of the solution times 100 all over 1. And of course, solution is solid plus solvent. So if I tell you that 40 grams of magnesium hydroxide dissolve in 100 grams of water. So 40 grams of magnesium hydroxide, that's already the solid. 100 grams of water, that is already the solvent. So for me to calculate the percentage of the solid, which is sodium hydroxide, will be 40 divided by 100 plus 40 times 100 all over 1. And the same thing is applicable to the percentage by mass of the solvent. The percentage by mass of the solvent is going to be the solvent all over the solution times 100 all over 1. So that settles percentage by mass of solid or percentage by mass of solvent, as the case may be. So now that takes us to the next fact, which is called molarity. Molarity of a solution. Now, what is the molarity of a solution? The molarity of a solution is simply the number of moles in solid present in 1 dm cube of a solution. The number of moles in solid present in 1 dm cube of a solution. So if I take sodium hydroxide in moles and I dissolve in 1 dm cube of a solution, that is what you refer to as in 1 dm cube of a solvent that forms a solution, that you refer to as molarity, and it's usually measured in mole per dm cube or capital M, also called molar. And the formula for molarity is simply 1000 times the mass of the solid all over the mass of the solution times the molar mass of the solid. Mass of the solution, take note, mass of the solution, sorry, volume of the solution, I beg your pardon, not mass. Volume of the solution. So molarity is 1000 times the mass of the solid all over the volume of the solution times the mass, times the molar mass of the solid. So the solution there is actually the solid volume plus the solvent volume. You got to put those two together to get the volume of the solution if the volume of the solution is not given to you. Very, very key and very, very sacrosanct. And also, the volume of the solution can also be derived from density. When you are given the density of the solution instead of the volume. So you know the mass you know the density, you can actually get the volume from there, because you can just divide the mass by the density and that gives you the volume of the solution. So you have to remember that vividly. Molarity of a solution is simply the number of moles in solid present in 1 dm cube of a solution or 1 liter of a solution. All right, molarity of stock solution. Okay, before that, just assume you were given a question. Calculate the molarity of 400 cm cube solution containing 9.8 gram of calcium triisocarbonate 4 in water. Calcium triisocarbonate 4, 9.8 grams of calcium triisocarbonate 4 inside water. So calcium triisocarbonate 4 is the solid. You have to look for the mass of that solid, which is 9.8. You have to look for the molar mass of that calcium triisocarbonate 4, which is 100. Then you have to look for the volume of the water, which has been given to you as 400 cm cube. Now take note, that formula I gave you, which is 1000 times mass of the solid divided by the volume of the solution times the molar mass of the solid. The volume there is measured in centimeter cube, not decimeter cube. Centimeters cube, that is the essence of the 1000. The 1000 resolves the problem of converting it to dm cube. You get it? So if you are given volume in dm cube, automatically the 1000 becomes useless. You got to cancel it. If you are not given in dm cube but in cm cube, then you include the 1000. So here the volume given to us is a cm cube, so I'm going to use 1000 times 9.8 divided by 400 times 100, and that will give me 0.24 molar, or 0.24 mole per dm cube. Molarity of stock. A stock solution is simply a concentrated solution of a substance, usually highly concentrated, prepared in large quantities in the laboratory and be used bit by bit. In fact, it is stored in bottles. Very concentrated. At times you see like 20 molar. Very, very concentrated. So they store them in bottles and they are being used bit by bit by dissolving them for lab use. At times you can just go and sip 10 cm cube of 20 molar, and you have to dissolve it to a particular molarity that is suitable for the reaction you want to use it for. If maybe you're performing titration, for example, courtesy demands that you dissolve that 20 molar to about 0.05 molar, so that it will be a very, very weak concentration to have less harm to those who would drink acid in the process of performing titration. So, and for you to be able to know the quantity of molar volume you will sip from that stock and dissolve accurately, you will need the formula we call dilution formula. And dilution formula is VI times CI equals VF times CF. VI is the initial volume, CI is the initial concentration, VF is the final volume, CF is the final concentration. Very, very important. Next, the molarity of a stock solution is given by 10 times P times D divided by molar mass. The P there is the value of the percentage. I repeat, value of the percentage, not the percentage itself. If it is 20%, you are using your P as 20. Remove the percent, you remove the 100. D is the density of the solution in grams per cm cube or grams per milliliters. That is the unit of density in that formula. The 10 that you see there is actually the resolved version of the formula. So it is 10 times percentage times density of the stock divided by the molar mass of the stock. That will give you the molarity of that stock solution. Now, if you're wondering where the 10 is coming from, just remember the initial formula, which is 1000 times percentage times density over molar mass. 1000 times P over 100, you get it? P over 100, because that's percentage, times density, which is in grams per cm cube, divided by molar mass, which is in grams per mole. And of course, the 100 at the bottom of the P will cancel the 1000 to give you 10. And then the grams from the density will cancel the grams from the molar mass at the bottom. So your answer is likely going to be in moles per cm cube. However, it is also molar. But if you want it in dm cube, you can always go ahead and do the needful with 1000 as the case may be. So, but your answer is always expressed in molar. Molar. Grams per cm cube is molarity. Just that we're not talking about, it's supposed to be in thousands of cm cube. All right, so that settles the aspect of molarity of stock solution. Now, exam question. What is the molarity of a stock solution of tetraoxosulfate 6 of density 1.84 grams per cm cube containing 98% by weight H2SO4? Calculate the molarity of a stock solution of H2SO4 of density 1.84 grams per cm cube. They've given you density, they've given you percentage as 98, and of course you know the molar mass of tetraoxosulfate 6 to be 98. Just do your division and you get 18.4 molar, as the case may be. Another exam question: what volume of stock solution of H2SO4 is required to prepare a 400 cm cube of 0.5 molar concentration of H2SO4? What volume of stock should I use to prepare 400 cm cube of 0.5 molar concentration of H2SO4? So what volume should I sip from that bottle of stock to prepare 400 cm cube of 0.5 molar H2SO4? And of course, you use your dilution formula. That has to give us the concentration of the stock, which is 20 molar, for example. So all I need to do is initial concentration 20 molar, initial volume, and that is what I'm looking for. Final volume 400 cm cube, but you convert it to dm cube anyway. Then the final concentration is 0.5 molar, and by the time you do that mathematics, you are going to have your value as 10 cm cube. That 10 cm cube you have is the volume of the stock you are going to sip. Then what is the volume of the water now? The volume of the water is not 400 because that solution from the stock plus the water is 400. So the volume of the water required is now that 400 minus 10 to make it 400. So by the time you dissolve that 10 cm cube inside 390, you will now have 400 cm cube of 0.5 molar H2SO4. I hope that's clear. Good. Another exam question can come up and say, what is the volume of water solution to be added to 300 cm cube of 0.5 molar HCl to dilute it to 0.05 molar? Listen attentively. What volume of water should be added to 300 cm cube? That means I have an existing concentration of 300 cm cube of 0.5 molar HCl, and I want to dilute it to 0.05. So the question now is, what volume of water should I add to that 300 cm cube existing solution? So what it simply means is that the initial volume is 300, the initial concentration is 0.5 molar, the final concentration is 0.05 molar, the initial volume is 300, while the final volume I'm going to get will be the volume of the water plus the existing concentration, which is 300. So at the end of the day, it's giving me 3000 cm cube. That 3000 cm cube is the volume of the water plus the 300 cm cube existing concentration. So the question did not ask me what is the final volume of both the water and the existing concentration. The question clearly asks for the volume of water that should be added to 300. So since I have calculated 3000 cm cube, I will subtract the volume of the existing concentration so that I will now have the volume of the water I am adding. And the volume of the water I'm adding there is 2700 cm cube. That's a smart question, bro. You just got to think about it. Next, the concentration in ions. Of course, if you are given H2SO4 at 0.5 molar and you are asked what is the concentration of hydrogen ion in 0.5 molar of H2SO4, all you need to do is to multiply the number, the basicity of that hydrogen ion, or the number of moles of the hydrogen ion, by the concentration of the tetraoxosulfate 6. So if it is 0.5 molar of tetraoxosulfate 6, what is the concentration of hydrogen ion? It's 2 times 0.5 molar, okay? And that will give me 1 molar concentration. The same thing happens to any other substance that you want to do. Just write a dissociation expression, write the number of moles where necessary, multiply by the number of moles, and that gives you that. And then also mole fraction, that you know already. The mole fraction of a given substance is simply the number of moles of that substance divided by the total number of moles into that particular stuff, as the case may be. So the next thing we are going to be talking about is molality. Very important. Molality. Molality. Molality is a very, very key area that we have to talk about, because molality is a very interesting part to deal with. Molality. So what is molality? Molality of a solution is simply the number of moles of solute present in 1 kilogram of a solvent. The number of moles of solute present in 1 kilogram of a solvent is called molality. It is measured in molal, and it is represented by small letter m. Molality, therefore, is given by 1,000 times the mass of the solid all over the mass of the solvent, which is Ws, times the molar mass of the solid. That 1,000 there is there to convert the mass of the solvent that is in grams to kilogram. You get it? So it's simply 1,000 times m divided by Ws times molar mass. And then, of course, we already know that mass over molar mass is number of moles, so you can just say n times 1,000 divided by the mass of the solvent. This is no longer solution, but mass of the solvent. So you have to be careful with that, mass of the solvent. For example, calculate the molarity of a solution containing 30 grams of potassium triisocarbonate 4 in 15 grams of water. 50 grams of water is the mass of the solvent, right? 30 grams of triisonitrile 5 is the mass of the solid, divided by this molar mass times by 1,000, and you get the answer there, right? Now, listen to this smart question. Calculate the molality of a solution prepared by bubbling 16 grams of SO2, that is sulfur 4 oxide, into 205 cm cube of water. Now, this is a very serious question. Calculate the molality of a solution prepared by bubbling 16 grams of sulfur 4 oxide into 205 cm cube of water. When you talk about molality, there are some key things you need. Number one, the mass of the solute, the molar mass of the solute, and the mass of the solvent. The solvent we are talking about here is water, and the volume given to us is 205 cm cube of water. That means the mass of water is 205 grams. Why? Because 1 gram of water, it occupies 1 cm cube. That's the gospel truth. So 1,000 grams of water, which is 1 kilogram, will occupy 1,000 cm cube, which is 1 dm cube. So just convert the number of volume into grams, and that tells you the mass of the water, right? Now, what about the solid? Can we declare sulfur 4 oxide a solid? No. Sulfur 4 oxide is not the solid. It is just a gas that is bubbled into water. The solute is now formed and remains into water. Now the big question is, what is the solid form and remain into water? H2SO3, sulfurous acid. Yes, because sulfur 4 oxide is an acid anhydride. Once it dissolves in water, it forms a weak acid. And that weak acid becomes the solvent inside the water. Did I say the solvent? The solute inside the water. And of course, for it to be formed simply means that it must have eaten part of water. It must have used part of water. It must have consumed part of water to form the weak acid that now dissolves in the water. So you have to know the amount of water that was consumed in the reaction, so that you don't end up using too much water as the mass of the solvent. You get it? And then from there, you can now compute the mass of the solvent or the solute produced inside the water. I think I'm making it a little bit complicated, but let me make it easier for you. The first thing to do is to write down your equation. And that is sulfur 4 oxide plus water to give you H2SO3. H2SO3 is the solute. And of course, if you balance the equation, it is a 1-to-1 mole reaction. 1 mole of sulfur 4, 1 mole of water, and 1 mole of sulfurous. And if you convert them to their masses, 64 grams of sulfur 4, 18 grams of water, and 82 grams of sulfurous acid. And of course, that obeys the law of conservation of mass. Good. But you are given 16 grams of sulfur 4 oxide. You are not given the gram of water that partook in the reaction. You can call it X. You are not given the mass of sulfurous oxide or sulfurous acid produced. You call it Y. So you can actually first of all compute sulfur 4 oxide and water to get the value of X through simple proportion. So if 64 grams of sulfur 4 could react completely with 18 grams of water, then 16 grams will react with how many? And that will give you a total of 4.5 grams of water. And that 4.5 grams of water is the amount of water used by the sulfurous acid. So for me to now predict the amount of sulfurous acid produced is through the law of conservation of mass, which is the mass of the product equals the mass of the reactant. So if I sum the mass of the reactant now, which is 16 plus 4.5, that will give me 20.5 grams, and that is the mass of the solvent, the solid produced sulfuric acid. So now that I have the mass of the solvent, the mass of the solid, which is 20.5 grams, the next thing I need is the mass of the solvent. The mass of the solvent can no longer be 205 cm cubed, which is 205 grams. Why? Because 4.5 grams of that water was used by sulfurous acid. And then on that note, what I am left with is 205 grams minus 4.5. That will give me 200.5 grams of water. And that is now the solvent holding the solute, which is the sulfurous acid. And then from there, you impute them into your formula. So your mass of the solid becomes 20.5. The mass of your solvent becomes 200.5, while the molar mass of your solute, which is sulfurous acid, is 82. And boom, your answer becomes 1.25 molal, or simply with small letter m, right? All right, so that answers that. That takes us to the last part, which is normality. Normality. Now, Juriben, what is normality? Normality of a solution is simply the number of equivalent solutes present in 1 dm cube or 1 liter of a solution. The number of equivalent solutes present in 1 dm cube or 1 liter of a solution. Its definition is just the same with that of molarity. In molarity, you talk about 1 mole of a solid, but here you talk about number of equivalent solids present in 1 dm cube. And of course, it is measured in equivalent per dm cube, or simply equivalent per liters. And then it is represented by a capital letter N, which is normal. Normal, that's the name. Normality. From normality, you have normal. So what is the formula for normality? Normality is simply the product of molarity and the number of reacting units. That's the formula for molarity. Normality, I want to say. Molarity times the number of reacting unit. What is the number of reacting unit? Number of reacting units depends on whether the substance is an acid or a base or a redox substance. For example, if it is an acid, it is simply the basicity of that acid. H2SO4 has a normality of 2. HCl has a normality of 1. If it is a base, we're talking about the acidity of the base. Sodium hydroxide, for example, has a normality of 1. But calcium hydroxide has a normality of 2. If it is a redox substance, for example, KMNO4, then it is simply based on the number of electrons gained or the number of electron loss. That tells you the normality, that tells you the number of reacting units, not normality, please. That tells you the number of reacting units of that substance. For example, I have KMNO4, and in the product, I have manganese 2+. That means it has lost 2 electrons. Of course, at KMNO4, manganese there is 7+. And now in the product, it is 2+, meaning that it has gained how many electrons? 5 electrons, right? Just find the difference. That's 5 electrons. So the value of N, which is the reacting unit in that substance, is what? Is 5. And then also, if you have potassium dichromate 6, and then in the product, you have your chromate as 3+. From 6 to 3. What does that mean? It has lost how many? 3 electrons, right? Good. Or gained 3 electrons, as the case may be. But this time around, when you balance the reaction, it's going to be 2 chromates because it is dichromate in the reactant. So it's going to be 2 chromium ion, which is 2 chromium 3+. So that makes the total number of electrons gained or lost here to be how many? To be the total number of electrons gained to be 6. Because 1 atom of chromium in the reactant is 6+. In the product, 1 atom of chromium is 3+. 2 atoms of chromium is how many? 6. So that means that it has gained 6 electrons into 3 versions 2 times. You can't say it is 0. It cannot be 0 because the chromium we're talking about in the reactant is not 2. It's only 1 chromium. So 1 chromium is 6 plus 2 chromium is supposed to be 12 for it to be 0. You get it? So, but now we're talking about it being 6, and that is the explanation to it. If you don't understand, play it back. Now, let's go back to the formula or the definition of normality. Normality is simply, of a solution, is simply the number of reacting, did I say reacting unit? Normality of a solution is simply the number of equivalent solutes present in 1 dm cube of a solution. Number of equivalent solute present in 1 dm cube of a solution. Now the big question is, what is the number of equivalent solute? The number of equivalent solute is simply given mass all over the equivalent mass. And then another question may pop up. What is equivalent mass? Equivalent mass is simply molar mass all over the number of reacting units N. And the big question is, what is the number of reacting units? We have done that before. In an acid, basicity; in a base, acidity; in a redox, electron gain or electron loss. Normality. So number of equivalent is simply given mass all over equivalent mass. While the equivalent mass at the bottom is simply molar mass all over the number of reacting units. So one can write the number of equivalents of a substance to simply be the mass of that substance times the number of reacting units all over the molar mass of that substance. Or simply put, number of moles times the number of reacting units. I use N hyphen to represent number of reacting units. And take note, the normality of a substance can also be equal to the molarity of a substance, and that can only happen when the number of reacting units is equal to 1. For example, HCl. HCl has a number of reacting units to be equal to 1, so automatically the molarity of HCl is equal to the normality of HCl. I'll give you a typical exam question. You are asked, 400 cm cube solution of HCl was prepared by dissolving 3.65 gram of HCl in water at 50 cm cube. Calculate the molarity of the solution. Of course, you have given me volume of the solution, you have given me the mass of the solid, and of course I can get my molarity, which is 1000 times 3.65 divided by 400 times this. Take note, 400 is in cm cube, right? Because there is 1000. All right. So that gives me 0.25 molar. That is the molarity of HCl. If you're not asking me for the normality of HCl, normality is simply molarity times the number of reacting units. And the number of reacting units in HCl is 1. So 1 times the molarity is the same molarity, 0.25 molar. But this time around, you can call it normal because you're going to put N, a capital letter N, or put it as equivalence per liter. So, ladies and gentlemen, that's caused the end of this amazing chapter. And that is the end of stoichiometry. Yeah, we are finally done. In the next chapter, we are going to go into the realm of colligative properties. Thereafter, acid, bases, and salts, and acid-base reaction. Thank you for listening. Boom.